Okay. So let's chit chat a little bit. So, let's make sure everybody's cool with what you have and what I'm looking for on these diagrams. And yes, you make sure on Monday you bring a ruler and a sharp pencil because you're gonna have to draw ray diagrams, okay? So make sure that you have that. Yes?
Did I leave my ruler in here again? My math kit? Did you see it?
I didn't see it.
Oh my god. I'll be right back. Keep going.
Okay. All right. Thank you.
Gotta see if it's in the back of the room.
Okay, all right, so here's what you want to look for, like for example, on this right now. It's just funny because this kind of flipped me out when I saw this because it's just what you get used to. I always put my object over here and then I have it going like right to left.
That took me out.
They put it over here and you had to go that way,
I did leave it.
okay? So that just kind of, it's just like inclined planes. Whenever I draw inclined planes, I always draw them like that. If I drew them like that, it just flips me out, okay? So it's just whatever you get used to, that's all. All right, so on this one, you got the object. They kind of tell you what the scale is. So this is one of the more simple ones because it's a converging lens, right? So you just kind of need to come over here and go, okay, hey, this thing is going to come over like this, point. Okay, you got that action going. Draw it through that focal point. Make sure that you label, you've got that focal length, which is at 12. So it's going to go through something like this, and then you got that one going through the middle. So the minimum you need 2. Ideally, you would draw all 3 where it also goes through that focal length here and then across, but a minimum of 2, preferably 3. Now, let's talk about this one in terms of what's going to happen with these lenses, and that's what I kind of tried to explain yesterday. So when this thing's going to hit, the first thing you want to look at is that you're going to have that angle that's going to be at a right angle to this. So this one is in lens in the air. So air has the smallest index of refraction, which has a value of 1. So it's going to hit this, right? And then it's going to slow down. So when it hits this, is it going to get bent up or is it going to get bent down? It's going to get bent down, right? Now, you don't know enough values to actually calculate. All you're looking for is like a qualitative drawing. It's like, okay, so this is going to bend down like this, right? So you got that action going, right? Now, then you need to draw a second normal line. And that second normal line is going to be like this, okay? So it's going to go like that. Okay? Now, when it hits back into the air, what's going to happen? It's going to speed up. So is it going to go up or is it going to go down? It's going to go down, right? So it's going to go, because it's going to speed up even more. So it's going to be something like this, okay? So now, what we typically draw is that we just do the voodoo that we do up here, and we just draw it bending one time. In reality, it actually bends twice, okay? So this is actually more of a representative of what's going to take place. Now with this one, and this is where you want to look at what's going to be similar and what's going to be different. You're still going to have even though this is in water, so that light is traveling slower when it gets to this point. So when you draw this, you're going to have this line here the exact same, because it's still the same normal line to the lens. Okay? So that's going to be the same. Actually, I want to try something. Okay, I thought it was going to be something cool, but it didn't work. Okay, so you're going to have the exact same normal line, but here's the deal. Because of the fact that this is going slower, right, and this is what we went through the math yesterday, because if the index of refraction of this fluid was the exact same as the index of refraction of this lens, what would the light do?
It'd be just go straight
It
through.
would just go straight through, right? So since you have a smaller difference between the index of refraction, what's going to happen to this angle? Is it going to bend more steeply, or is it going to bend less steep?
Less steep.
It's going to bend less steep because there's a smaller difference in that index of refraction. So over here, I'm going to draw this just a little bit more shallow than what you did here, okay? Because you have a smaller difference in those index of refractions, right? Now, when it leaves, again, now you've got to draw a second normal line, but this normal line, okay, is still going to be at right angles to this lens, but now when it exits out, okay, because now you're going into a smaller difference in the index of refractions, is it going to bend more steeply than this one or less steep? Less steep, because there's a smaller difference, right? So when you draw this one, you're going to draw that one a little bit more shallow, okay? Now remember, this lens, this rays, because of this lens, wants to go through the focal point. So this one is trying to go through the focal point where it would be right here. This one is going to try and go through the focal point, but because of this difference, it's going to end up, that focal point's going to get shifted way out here. Because if you think about it, if these were the same indexes of refraction, it would never go through the focal point because it would never bend. It would just keep going parallel with it. So you got this, boom, there you go. So when you get to that question, describe how the focal length, lens, position, size of the image form. Now you want to, there's two things that you want to think through, okay? Number one, what's going to happen to the focal length, where it's going to go, and then what's going to happen to the size of the image. Now keep in mind, come up here, so use this one as like a model. So imagine that you shift that focal length out here. Okay? Imagine that you shift that one, that focal length now gets shifted out here. You're still going to have that one that's going to go through the middle. So go up here and look at this and go, okay, if you wanted to, you could just maybe lightly sketch it and go, okay, this line is still going to be coming through here, but now it's going to end up out here. Then take this one and draw it, and then say, okay, where's it going to meet? Based upon where it's going to meet, what's going to happen to the size of that image? Okay? So that's what you want to be able to think through. Okay? Are we good? Anything else you want me to go over on the lab?
3A.
3A?
Yeah.
Like what it's going to look like?
Yeah, we had debate.
Okay. I'll give you a hint. It gets flipped on both axes. So it gets flipped on the x-axis because it's going to cross in like both directions.
Wait, so I had it drawn like this.
Huh?
I had it drawn like that.
Yeah, you're good. You're good.
Wait, can you elaborate on what you just said?
Huh?
It's gonna cross what you mean when, like, you said cross in both directions.
So it's going to cross on, so it's going to get flipped vertically,
Right, but like,
and it's also going to get crossed.
how do you know that?
You don't have to draw the scale.
Well, part of it is that you did this on the lab earlier. That's why I had you draw the lab
That's
so
what I
you
did
could
with
actually
mine.
see it.
Well, right, but that was yeah, anyway.
It was the exact same lens.
Yeah, okay, yep, I got it.
I
Thanks.
think maybe she's asking what would indicate that it would do that.
Oh, it's just because that's what's going to happen when you have a
It's just 'cause
convex
that's gonna
lens.
happen.
It's going to, you just have to know that it's just going to swap it on both axes. But mirrors only swap it along like the y-axis, like you get when you look at a mirror. you get switched this way, but you don't get switched along an x-axis. Lenses like that is going to swap both sides.
All lenses?
Yeah,
Okay.
that's going to be a situation like this, yeah. Okay. All right. Now anything else? Going once? Going twice? So, it's like 3 multiple choice questions. So, go ahead and give them a try, see what you come up with. That way I can go in and edit that part. Okay, so here's the deal. So one of the things that you're going to have to figure out right from the get-go as you prepare for this test is what's going to be positive, what's going to be negative, depending upon the lenses, depending upon the mirrors, okay?
Oh, Kelsey's gonna explode.
You're gonna die. Sorry.
I liked how Gannon's immediate reaction was, oh, he's gonna explode.
That was the running joke in English 10 Ways.
It's my insulin pump.
Okay. So is your object distance always positive, always negative, or it depends?
Always positive.
Always positive. So this is the one that's always a positive number, okay? There's no thinking on that, okay? What about your focal length?
It could be positive or negative.
Can be positive or negative. Party girl, in which situation am I going to have a positive focal length?
What are my options?
Concave mirror, convex mirror.
Concave.
Why?
Goes in.
It's bringing it together, right? Okay? So anytime the light is being brought together, that's like a positive influence, right? People like to be around people, positive things happen when people bring people together. Okay? Party girl?
Yeah.
Concave lens, convex lens.
Concave.
Beautiful. So that's the disparity. So you're going to have a positive focal length when you have a concave mirror, okay, or a convex lens, okay? You have to know that, okay? Make an index card, whatever, okay? That is something you have to know without fail, okay? You just have to know it. So, in this situation, you've got a diverging lens. A diverging lens is the same thing as what? A convex lens or a concave lens? Concave, convex? Concave, right? So this lens is going to be like this. So this light's going to hit and it's going to scatter. But part of that is going to get reflected back to form an image over here, right? So, with that being said, you've got this image is going to be over here. Is it going to be upright or is it going to be inverted? It's going to be upright. Is it going to be real or is it going to be virtual?
Virtual.
Virtual image. Is it going to be bigger or is it going to be smaller?
Smaller.
It's going to be smaller. So like you cannot project that onto a screen. Okay? All right, I just got the text. I got to go call Washington. I'll be right back. Stop that. With all of that said, what's your answer to A?
A.
Okay.
A. The first question is A. All right. Now, how would this, so if let's say you don't know, here's what you could have done. You could like play the numbers game. So you got 5 centimeters away, focal length of 10 centimeters. You didn't actually have to do the calculations, but since you gave the numbers, they could. Okay? Now, what's important is that you got a focal length of 10 and it's 5 centimeters away. So is the 5 centimeters away your object distance or your image distance?
Object distance.
That's your object distance. So you could go through and you could calculate the image distance. So what you would see, if you did that, you would get an image distance of negative 3.33 centimeters, which would then allow you to calculate the magnification. So then your magnification would be a negative of a negative 3.33 divided by 5, which is your object distance, okay? And that would get you 0.67. So that's a positive magnification. So when you have a positive magnification, that indicates that it's what?
Upright.
Upright, okay? The positive doesn't indicate real or virtual, okay? That just tells you that it's upright, okay? All right, so we got that one. Now, had this been a converging lens, okay, what's the only thing that would have changed?
That's real.
Yeah, okay, the light would be going through, right? So when you do the calculations, if it had been a converging lens, the focal length would be, instead of being a negative number, would have been a positive number, okay? All right, and the image would have showed up on the other side. It would have been upside down, but it would have been a real image where you could project it, okay? Now, with converging lenses, I'm going to tell you right now what I won't do, okay? Because converging lenses get a little bit weird, because sometimes you can get like a virtual image that's on this side of it. That gets really weird and kind of tough to draw. So if there's one that I probably won't emphasize, it's going to be that one. Probably with a converging lens, most likely it's going to be somewhere over on the other side, okay? So just keep that in mind. All right, so speaking of converging lenses, what'd you get for the second question? A, why?
Because it's going to be inverted because it's a converging lens.
Yep.
And then it's always going to get smaller because it's in front of the focal point.
Okay,
Or I think it was. Yeah, it's in front of the focal point, so it gets smaller. Yep, sorry.
okay, now, with this one, because of the fact that you can actually calculate the magnification, on this one you'd actually want to run the numbers. So what I would recommend on this one, again, you're going to start with 1 over psi plus 1 over so equals 1 over your focal length. So you've got the focal length, you got your object distance. Typically, on a problem like this, you're going to solve for your image distance. Now, here's the whole kicker. On this one, that focal length is going to be a positive value because it's bringing that light together, okay? So with that focal length being positive, then if you do the math, you get an image distance of 6 centimeters. Now, here's what's important in terms of the contrast. With this one up here, this image distance here was a negative value because the light was going in this direction, but the image was caused by part of that light being reflected back, and you're here. So if this one, that image distance being a negative value, it's negative because it's in the opposite direction that that light is really going. Yes?
So this is kind of an obvious question, I feel like, but I just want to double check for myself. So
Okay.
are all virtual images, will they all have a negative image distance if it's virtual?
I'll get back to you on that one. So you're asking what?
Will all virtual images have a negative image distance or no?
Yes.
Okay,
I won't say that. I can't think of an exception right off the top of my head.
okay,
Okay.
thank you.
All right. Now, so with this one though, since the light is going in this direction, so the light's going like this way, right? And the image is in that same direction that the light is going. This one, you end up with if you go through the math, this one you get a positive image distance. Because the light's going this way, that image is over there. Okay? So, cool with that. All right. Now, let's talk about this last one with this idea of total internal reflection. So actually, let me go get the laser and I'll try and do this up here.
Yeah,
Oh, you didn't like that?
no.
Okay. Hopefully you can see this.
Should you have your phone over here, just
Huh?
in case?
Well, I've got it on, like, it would ring.
Oh, okay, I was
You
like,
do.
wait.
Yeah. Okay. So. Okay. So this is actually one of the questions that's part of this review. And you're trying to find the index of refraction. So notice if I shine that laser straight, okay, I'm hitting it from this side, and it's going from air into this acrylic. So it slows down when it hits that acrylic. So what happens on this data table, this is on that second page that I gave you. So what you're doing is you're shining this around, and what you're keeping track of is that angle of incidence versus that angle of refraction. So as you go around, and here's the other thing that you'll see, is that going around like this, you'll notice that that never gets totally reflected back in, okay? Part of it does through, right? Part of it is also being reflected back. So you have some that's going through and you have some that's being reflected. But now if I change it, now I'm going to go from the curved surface to this flat surface. So what that light is going to try and do, and this is relevant to that last question. So with this one, that light is trying to go from this acrylic out into the air, okay? But if with this one, I'm going from the air into the acrylic, right? This one is trying to go from the acrylic into the air. So when you talk about total internal reflection, that's only going to happen when you're going from a more optically dense medium into a less optically dense medium. So what I'm going to try, and hopefully you all can see this. So I'm going to spin this around, and what will happen is that you'll get that point. See, if I'm above that angle, that light's going through. But if I hit that angle and go beyond that, then all that light gets reflected back. And that's that critical angle where you have total internal reflection. But that only happens when you're going from a more optically dense medium into a less optically dense medium. So if I go like this, where I'm going from air into the acrylic, there's no point on here that I can get where all of that gets reflected back. It's all, some of that light's always going to be going through because I'm going from air into the acrylic. But if I change it, and if you look at that interface up here, where it's trying to go from that acrylic into the air, that's when you can hit that critical angle and make it totally reflect within that. So you're here, boink, you get that point. So you can also get it where if you hold it just right, where it actually kind of runs parallel with that, but then when you go beyond that, then all of that light gets reflected in, and that's what's happening down there. Got the visual. Okay. What's that?
So then if this one's going from air into glass, then it couldn't have any internal reflection? Or total internal reflection?
Hold on.
Okay.
What?
I said, so since this one's going from air into glass, then it couldn't have any total internal
No.
reflection?
So on that question, because you're going from air into water, you could never, that's what I was trying to show you, you could never reach a point where you have total internal reflection. It's not going to happen, okay? Now, so if you look at this, get this, it's a sign of N over N naught, inverse sign.
No mirror, correct, go off.
What, you expect to see too? Come on.
Well, this is the optical.
I know. So, or is that N naught over N? Oh, it's N naught over N, my bad. So here's the deal. So with this one, it's this inverse sign of N naught over N. And if you need this equation, I will give it to you on the test. Don't memorize it. Okay, if you need this equation, I will give it to you. So, but here's what you do need to say, or realize on this one, that if you look at what could potentially happen, and you got to understand the difference between reflection and refraction. Okay, so refraction is when the light still goes through, but it just gets bent. Reflection is what happens when a mirror, when you're going to get that bounced off. So you got the light ray will reflect, but not refract. Well, the only way that it could reflect is if it hit this surface and it acted like a mirror, and all of that got bounced back. Is that what's going to happen? No, so it can't be A, right? So then you get B, the light will refract, but not reflect. So anytime you're going into like this transition, you always have some of that light that gets bounced back. And that's what I was trying to show you with that piece of acrylic, okay? Some of that, and this is what allows you to have, this process is what allows you to have like a convex lens where it scatters that light, but yet you're still able to form that image here because it's mostly being refracted, but some of it's being reflected. Because if this concave lens refracted all of it, and all of that light went completely through it, you would never be able to form an image here. If all of that light went through it, you would never see anything over here. It would all be going through. Okay? Go with that one. So it can't be B.
Okay, so just to clarify, it is in over in not, right?
Huh?
It is in over in not.
Yes. So, because with this one, and that's what we'll get into. So, you got C, the light ray may undergo internal reflection in the air if theta n exceeds the critical one. So, with this one, because of the fact that you're going from air into water, right? So, that can't happen because of the fact that there's no angle where that will take place. So, it can't be C. Can't be D, the right may go total if the theta n is less than that, that has nothing to do with it. So you're basically, the only one that's true on that second question is B. Okay. Now, but let's play the what if game. What if we were going from here, we were shining that light in the opposite direction? Okay? And that's what I tried to show you with that piece of acrylic. If I'm going like this, if I'm starting here, then could there be a critical angle? Yes. So let's say do they give you the indexes of refraction? No. I just made up numbers. It's okay. So let's say that we're going to try where you're going to have, it's actually, yeah, okay. So we have the inverse sine of 1 divided by 1.5. It's actually n naught over, it's n over n naught. I'm trying to do that from memory. Okay? So, if that bottom one has an index of refraction of 1.5, right? And that top has an index of refraction of 1. And if you take the inverse sine of this, you should get like 40 degrees. So what that means is this, if you shine that thing at a 40-degree angle, then you would have a situation where all of that light is going to get reflected within that if you're going in this direction. If you're going in that direction, it's never going to happen. Okay? Got that? We're good? Great. Okay. So,
What's the answer?
huh?
What's the answer?
To this one is B.
Oh, you said he was wrong.
I also heard B was wrong. Yeah, I thought you said B was impossible.
No, I'm sorry. No, B is the one that's right.
So it can't reflect?
Hold on.
I thought it was E. I have E circled. Is it not E?
It is E. I'm
Okay,
sorry.
I was like-
looking at the wrong one. It is E. My bad.
I know. I was like, I can't believe I got it right. And then you're
Okay.
like, so the correct
I'm
answer
sorry.
is B.
I was
and I was
confusing
like,
B with
what?
E and trying to keep track of the phone, and I'm pissed because I hate it when people don't make sense. Yeah. So, okay.
That's good.
All right, there we go. All right, so now try that next one with the chart.
Stop the camera.
Yeah. So you look at this in terms of, you're trying to find the index of refraction of the plastic, right? okay? So, is your index of refraction going to be bigger or smaller than 1?
Bigger.
Bigger.
Bigger, okay? So right away, you want to choose a set of data that when you find the slope, that you get an answer bigger than 1, okay? Makes sense. So if you look at the relationship, okay, that you have, where you have like n of the air times sine theta of the air is going to equal n of the plastic sine theta of the plastic, right? Okay? So which means you can either have a ratio of the indexes of refractions, or you can have a ratio of the indexes of sine, okay? That's basically what you got. So since you don't have the indexes of the refraction, guess what? That leaves you stuck with the ratio of
Fine.
the sines, okay? Just think this through. So when you get to that point, then, so what did you pick, what did you put on each axis then?
The x was sine of index of, or angle of refraction, and then y.
Sine theta of r, right?
Sine
And then
theta of I.
sine theta of I, right? And depending upon how you choose your scale, it's going to be something like this, okay? Cool with that. So you should get a slope of around 1.4, okay? Which makes sense. Okay, all right, that's 1.4. Now, here's the deal. Think about this. Let's say that you were going to have a bigger index of refraction. Okay, that's 1.4. So let's say you had something that had a bigger index of refraction. So which of these data sets would be changed if you were dealing with something that had a bigger index of refraction? What would change?
The
Sine
I.
R.
Sine I. Sine I would make the slope steeper.
No, hold on just a second. I'm going to talk about physically what you would keep the same in the lab.
Theta I.
Yeah, you'd keep theta I the same, right? You'd still set it at 15, 30, 40, okay? You'd still set those same angles, right? Okay? But then what's going to happen if you have a bigger index of refraction? What's going to happen to these set of values here?
They're gonna get bigger.
Are they going to get bigger or are they going to get smaller? So look at how this deal is playing out, right?
Oh, they're gonna get smaller.
So if this comes in at that same angle and you have a bigger index of refraction, right? So if this is more optically dense, is it going to get bent more or is it going to get bent less? It's going to get bent more, right? So what's going to happen to these angles?
Smaller.
It's going to get smaller, right? So you're going to be taking the sine of a smaller angle. So look at this. Look at this general trend, right? So sine of 10 was, 0.17, 21, okay? So if these angles are getting smaller, first off, what's going to happen to the slope of this line? It's got to get, if you have a bigger index of refraction, the slope of this line has to get steeper. So if you keep the same theta I, that means these values here have to get smaller. Now, if these get smaller though, wouldn't that pull that down? Here's the point, okay? You want a bigger index of refraction, right? If this slope represents index of refraction, that line would have to become more steep, right? So if you're keeping the same theta I to get a steeper line, you'd have to have a bigger value of theta R to make that line become more steep. Okay? So that's what you want to be able to think through and say, okay, great, here's this set of data, but what's going to happen if you change this? What happens if you have a bigger index of refraction? What happens if you have a smaller index of refraction? Okay, so we got that. We already did that. That's that index of refraction, okay, around 1.4. Now, so this is what I tried to show you in terms of how you can change this up. So with this one, what you would want to do then is a way that you could verify that is you're going to shine it like this. So now you're going to try and hit that back side, okay? where it's gonna hit this backside, then it's gonna come down here like this. So because of the fact that you're looking at that interface from going from a more optically dense into a less optically dense, right? So if you could find that angle, so what you would want to do on that one where it says describe one experiment using measure the critical angle to indicate how the index of refraction can be determined from this measurement. Well, so if you look at how you calculate the index of refraction, so if you could measure that critical angle and you know that this is going into air, okay, so you're going to know that one. So then you can take that equation to find the index, knowing that critical angle for the index of refraction, you can work backwards and find that angle right there. So that's what you would have to be able to articulate. I won't make you, I promise you on the test, I won't, like I said, if you need that actual equation for index of refraction, excuse me, for the critical angle, I will give you that, okay? So don't memorize it. If you need it, I will put it on the front of the test, okay? All right. So let's say that I give you a concave mirror. Now, what do you know about concave mirrors? What makes concave mirrors different from convex mirrors?
Focus the light.
What did you say, buddy?
They focus the light.
It focuses the light. Okay, that's true.
They converge it.
You the light converges.
It makes it real.
So what's the sign of the focal length?
Positive.
Positive. Okay, always positive?
Yes.
Yeah.
Yep, always positive. So, but concave mirrors are unique because what can they do?
They can create real.
They can create real images and they also can create virtual images. Okay? One is upright, one is
Upside down.
upside down. Okay? So that's what you've got to be able to think through. So let's say that you have a candle out here at 30 centimeters and you have a focal length of 10 centimeters. Okay? So what I would be able to expect you to do on the test, number one, is draw the ray diagrams for this situation, calculate the magnification, and calculate the image distance. So, go. So, what'd you get for your image distance?
Like 15.
Beautiful. Okay? Now, what I do personally, this is what I always do on mirrors. This is what I do personally. First thing I do is I make this symmetrical down here, and I draw that one that hits in the middle, and then I flip that, and then, so what that tells me is that this image is either going to be somewhere in here, or it's going to be somewhere over there. Okay? That tells me exactly where it's got to be, right? So, it's either here, or it's there. Okay? It can't be down here, it can't be up here, it has to be here, or it has to be there. Now, because of the fact that if you do the math, you get an image distance of 15, so that tells me I got a focal length of 10, so this is going to be down here like this. So, if you come in here and draw one parallel, and then put one through that focal length, that wasn't bad for just doing it. Okay? Boom. So there's two. If you really want to make sure, draw three. Okay, so you got that one. Magnification. What'd you get for that?
Negative 0.5.
Negative 0.5. So that magnification is negative 0.5, which indicates what?
It's inverted.
It's an inverted. If it was a 2 centimeter tall candle, it would appear as 1 centimeter. And it is a real because I can project that onto a screen. Okay? Good with that one. Now, what if we did this? What if we reversed it? What if we took the same mirror, but we put the object at 15 centimeters, and it had a focal length of 30 centimeters. Now go. No, that's 10 centimeters, my bad. Okay, so in the name of time, Buddy, start that back up again. Okay, so in the name of time, with this one, and here's the difference. Now that image is going to be back here. So keep in mind, your eyeball is still here. So your eyeball is picking up these reflective rays, but it's going to make it look like it's back here. So if you're putting on makeup, this has two advantages. Number one, you get an image that's upright. Number two, you get an image that's bigger than what you're looking at. Okay? So this is why if you're going to look at a makeup mirror, okay, you want a concave mirror that has a long focal length where you can be inside of that, because that will project it, that will allow you to see an image that's magnified and upright. So, what did you get from the magnification? What'd you get?
Oh wait, for magnification.
Magnification should give like 1.5. Positive or negative? Positive, so therefore it is upright. So, the beauty of this test is you've got the index of refraction, and then you've got two concave mirrors, and you have two convex, excuse me, a concave and a convex mirror, a concave and a convex lens. Now, I'm also going to send out the answer key to an assignment that I typically give, but they're all problems out of the book. I'm going to send out the answer key to those problems. I promise you, you're going to have a problem where you're going to have a mirror, and you're going to have to shine a laser, and you're going to have to figure out where to shine that laser. Okay? There was one of those on that first assignment that I gave out. There's going to be one on this. Okay? I promise you there's going to be a problem like that on the test. The whole key to this is that these angles are symmetrical. Okay? Use tangents. All right? So, I promise you there's going to be a problem like that on the test. And I will send out the answer key to those problems. Okay, I will see you all on Monday.